Lecture 8 extends the discussion of mechanics from motion along straight line, or what we technically call linear or translational motion, to circular motion, or what literature also calls angular or rotational motion. Of course, the discussion on circular motion is not something totally new to us, for we have talked a little about this in lecture 4.5. In this lecture series, we will extend that discussion to describe more general phenomena pertaining to the mechanics of rotational motion. What are the equivalent to Newton's law of motion in rotational dynamics, for instance? So let's start our discussion from where we left in lecture 4.5. Remember this image? We use this image to illustrate the different terms in motion as the car is turning. Let's recap those terms. First, as the car turns, you may describe its displacement in terms of its angular displacement, that is how many degrees it has turned, or the displacement along the circumference of the track, which is technically called the tangential displacement. From these two types of displacement, two types of velocity are defined as displacement over time. Those are angular velocity and tangential velocity, respectively. We keep to the convention that negative angular velocity refers to clockwise rotation. We then derive the equation for centripetal acceleration, directed radially toward the center of the rotation. This is an acceleration responsible for the change in direction of the tangential speed, but does not affect the magnitude of the speed. Hence, in uniform circular motion, only centripetal acceleration is present. What we did not discuss then was what happens if someone turns the car while pressing on the accelerator at the same time. The answer should be obvious. The car will undergo not only centripetal acceleration along the radial direction, but it will also accelerate along the circumference of the track. Through the same argument, the latter acceleration can be described in the form of angular acceleration, or tangential acceleration. Notice how angular acceleration and tangential acceleration is derived as the difference in angular velocity and tangential velocity respectively over time, exactly just like how acceleration is defined in linear accelerated motion. Angular acceleration is denoted using the Greek letter alpha, and it carries the SI unit radian per second square. Same as in our discussion with accelerated motion, as far as this course is concerned, we will only discuss cases involving constant angular acceleration. That is to say, the object may rotate faster and faster, but it rotates faster and faster at constant rate. Now there is another type of motion in rotational mechanics, but to discuss this last type of motion, we have to look at another illustration, the wheel of a moving car. Again, let's recap the different motion we have learned and tabulated just now, which is present in the car tire. As you can imagine, as the car moving forward, every point on the tire except for one point which is exactly at the center of the tire undergoes tangential motion and angular motion. If the car is moving at constant speed, then we will stop our discussion at angular and tangential velocity of the tire. But if the car is accelerating, then it makes sense to talk about angular and tangential acceleration of the tire. Any rotating object also experiences centripetal acceleration. Thus, every point on the tire, except for the one point at the center of the tire, experiences centripetal acceleration. Up to now, there is nothing new. What is new now is that the car is moving as a whole. If we pay our attention back to the tire, this time around, this motion affects the one point at the center of the tire, the center of rotation of the tire. Hence, it makes sense to talk about the center of rotation velocity of the car's tire, which essentially is the velocity of the car as a whole. I will denote this as VCOR. COR stands for center of rotation, obviously. At this point, I could imagine some of you may be confused. Some of you may say like, huh, what this guy is talking about? Some other may think, yeah, this is obvious, so what? Or some of you who are critical may start thinking, isn't this VCOR the same as V tangential? If the car is moving at 100 km an hour, doesn't that mean the tires are rotating at tangential speed 100 km an hour? Oh wait, is it true? Well, hang on for the moment. I will come back to this slide toward the end of this lecture. I will explain the significance of me introducing all these motions then. But for now, let's save our attention to cogs and wheels. Cogs and wheels are used in the industry to transfer Well, let's just say in layman terms, mechanical motion from one object to another. Technically speaking, we do not transfer motion, we transfer momentum and energy. But well, you guys know what I'm talking about. Anyway, they work mainly based on two principles. One, they share the same axle, or two, when they are in contact at the circumference. In the former case, since both wheels have the same axle, it shouldn't take much imagination that when the axle turns, say by x degree, both wheels will also turn by the exact same x degrees. Hence, both wheels will experience the same angular motion, resulting in the different tangential motion if the wheels have different radii. The wheel with smaller radius has smaller tangential speed than the wheel with larger radius in accordance to this equation. In the second case, as the wheels touch each other on the circumferences, the turning of one wheel will cause the turning of the other wheel on the same tangential speed as the former. Depending on the engineering design, some are shown in this slide, one is able to transfer energy and momentum from one orientation to another. For instance, this particular contraption transfers rotation along horizontal axis to rotation about vertical axis. In any case, one thing is clear. Wheels or cogs who are in contact at the circumference will move at the same tangential speed. Please note that I use the term tangential speed, not tangential velocity, because depending on their engineering design, the cogs, such as the one on the rightmost figure, do not turn in the same direction, but they are turning at the same speed. This further means cogs with smaller radii will have larger angular speed than cogs with larger radii. This is the physical principle behind a fixed gear bicycle. The cog at the rear sprocket is designed to have smaller radius than the cog at the front or pedal sprocket. Of course, in a bicycle, these cogs do not touch each other at the circumference, but they are connected through a chain which essentially carries the tangential speeds of the pedal cog to the rear cog. The rear cog then drives the rear wheel. A slight turn on the pedal sprocket will translate into a large turn on the rear sprocket cog, which further means a large turn of the rear wheel as a whole. A racing bike or mountain bike is normally equipped with multiple gears, which enable the cyclist to adjust the radius of the pedal and rear sprocket cogs on which the chain is latched. This thus enables the cyclist whether to latch the chains on smaller cogs to increase speed when riding on a smooth flat surface or downslope, or larger cogs to increase torque at the expense of speed when going upslope or rocky path. Notice that this design also enables both sprockets to turn in the same direction, albeit of different angular speed. Of course, both sprockets must turn in the same direction, or else the cyclist will be in trouble. Designing and engineering gears for mechanical purpose is not a trait of the past. Scientists are still working on it, on a much smaller scale, I would say. This slide shows two molecular gears made of fullerene. Fullerene is a relatively big and stable molecule, which is made of 60 carbon atoms. Interestingly, these carbon atoms bind to each other to form a ball-like structure. So you can imagine that at every corner of this molecular structure stands a carbon atom. And each of the edges in the structure represents the covalent bond between carbon atoms. These covalent bonds are relatively strong, resulting in a stable molecule as a whole. Scientists is thus able to use this structure as building blocks, like Lego blocks, to build larger molecular objects, such as this nanocog. Isn't this cool? Okay, enough with cogs and wheels. Let's get back to our moving car illustration to discuss the last point from this lecture, the concept of rolling without slipping. Rolling without slipping is a particular term used to describe the condition where the tangential motion of the tire is equal to the center of rotation motion of it. That means if the tire has turned by, say, 20 meters, of course given the radius of the tire we can compute its circumference, and we can then compute how many times the tire has turned to accomplish 20 meters. But yeah, let's say the tire has turned 20 meters. The center of rotation of the tire, which also means the car itself as a whole, has also moved by 20 meters. If the process takes 2 seconds to complete, for example, that means both the tangential speed and center of rotation speed of the tire is 10 meters per second. The car travels at 10 meters per second as a whole. That is, both the tangential and center of rotation speed of the tire are the same. Now you may think that, isn't this obvious? Aren't all cars along Kent Ridge roads move this way? Well, I'll tell you not necessarily. Have you ever seen a car braking suddenly? When a car brakes, its center of rotation is still moving, but the tire is no longer turning because the braking mechanism locks the tire. Well, that's what a braking system is supposed to do after all. As a result, the center of rotation of the tire moves faster than its tangential speed, a condition which literature typically refers as sliding or skidding. Or another example is when the tire is stuck deep in the mud or snow. You can imagine that the tire is turning vigorously, churning out those muds, but the center of rotation of the tire, and hence the whole car, does not move an inch. The tire slips on the mud. As a matter of fact, rolling without slipping is a special case which happens only in ideal situations. Generally, when a car is moving along an expressway, rolling and slipping or skidding are involved at the same time. This is what exhausts the tires after some time.